Welcome all. So, today we will continue and look into the different type of failure modes in the ductile materials. Last time we looked into the necking type of failures, we looked into the crack propagations, and we looked into the void formation and the coagulance failures. Okay. So, we will move ahead and look into the other type of failure modes occurring in the ductile materials. Okay. So, there is a failure mode which is known as the shear plugging and the plating. Okay. So, it normally occurs in the plate. Okay. So, what happens in thin ductile plates? So, this is observed in the thin ductile plates which are undergoing impact loading. Okay. So, shear plugging. So, what happens is that there is a disc type of failure zone occurs, which is due to the punching by the projectile. Okay. And pettaling occurs where pettaling like flap forms as the material tears apart. Okay. So, here we can see some sort of failure modes in the ductile materials. Okay. In addition to that, the high strain rate failure modes will occur, and localized intense shear deformation due to the thermal softening will also occur. Okay. So, here if we look into the figure 1, we can see a spalling occurs. So, a projectile hits the plate and there is a portion which is being teared off from the other surface. Okay. So, this is called a spalling type of fracture. Okay. After that, plugging will occur. Okay. What will happen is that the entire projectile will try to punch down entire piece of the material. Okay. And that piece is a resemblance of the shape of the puncture also. Okay. So, if you look into a ductile material, so first of all some sort of spalling will occur at the spall fracture will occur at the other ends. After that, as it tries to punch through, a similar piece will try to come out. Okay. And this type of thing is called plugging. After, and in some cases, okay, the cracks will form if this is the plate and if this puncture is occurring here. Okay. So, the cracks will form and they will form going out radially. Okay. So, these are the radial fractures that will occur. Okay. So, pettaling. So, in case of layered metals, what happens is that as the impactor tries to punch through, okay, this metal will try to form this type of small pieces type of form. Okay. So, this looks like a floral arrangement. Okay. Okay. So, this is type of pettaling, okay, which will occur on the top surface. Okay. Here we can see this type of floral fracture is occurring. Okay. So, these are nothing but the small top layers coming out. Okay. So, similarly, the pettaling can occur in the back surface also. Okay. So, this is the front pettaling and this is the reverse pettaling. Okay. And sometimes there will be a direct hole generation that will occur in the material also. Okay. Here we are looking into the adiabatic shear bending. Okay. So, what happens is that there is a high rate of strain failure mode and there is a localized intense shear distribution. Okay. Here we can see the material is failing in the shear mode. Okay. Here we can see the failure. Okay. And then the crack propagation. Okay. There is a bonding here and there is an adiabatic shear crack growth out here. Okay. So, these are the different ways in which the ductile materials will try to fail during a high localized impact event. So, dynamic properties. So, what are the dynamic properties? As we have seen earlier, most of the testing are done during a very slow rate of loading, and that we are considered as a quasi-static loading. Okay. So, most of the properties, the Young's modulus, the yield stress, the strain, that we saw that occurs under the slow rate of loading. Okay. So, whatever properties we have seen till now, okay, sigma, y, strain and all those things. So, the rate of loading is very slow or they are quasi-static. but during a dynamic event, okay, the rate of loading is very high. Okay. So, the dynamic properties changes during that time. Okay. So, we will try to evaluate what are the dynamic properties and how does the rate of loading affect the dynamic properties. Okay. So, strain rate sensitivity. So, what is strain rate sensitivity? So, the response of a material depends upon the speed at which it is deforming. Okay. So, ductile materials normally become stronger at high strain rates. Okay. So, we will look into this thing. So, dynamic yield strength, the stress at which a material begins to plastically deform increases with the increasing loading rate. It means that the value of the sigma y, okay, and so if this is the stress strain curve under slow rate of loading, this will try to behave like this. Okay. So, as we increase the rate of the loading, this type of behavior will be forming. Okay. So, this way the rate of loading is increased. So, here we can see the material is becoming stiffer as well as the sigma y is increasing and the ultimate stress is also increasing. Okay. So, increasing the rate of loading, the dynamic yield strength increases and the toughness also increases, it becomes stiffer and this ultimate strength also increases. Okay. So, the ability, so the dynamic toughness, that is the ability to absorb energy during rapid loading, which is critical for prevention of the catastrophic failure, it also changes or it is also affected by the increase in the rate of loading. Okay. So, these properties influence the energy dissipation, crack propagation and the structural stability during the dynamic event. Okay. So, what happens during a dynamic event? So, let us take a dynamic event such as an explosive event. So, here what is happening is that the blast waves, okay, they are being transferred to a simply supported beam system. Okay. So, these are the shock waves that are hitting my system. Okay. So, these shock waves, okay, they will act as a pressure loading on the system. Okay. So, on the back side, okay, I will see spalling of my system is occurring. Okay. Okay. After the spalling on the other side, okay, the compressive damage is also starting here. Okay. So, on the side of the blast waves, the compression loading is occurring and on the other side the tensile loading is occurring. So, in the tensile region I will see spalling starting to occur and on the same side the compressive damage will be observed. Okay. Okay. So, here compressive damage is being observed on the back side due to the tensile loading, the spalling is being observed. Okay. So, then the system will try to bend. Okay. So, on the other side flexural cracking will starts to propagate. Okay. And on the same side the compressive cracks will try to initiate. Okay. So, after that this shear compression damage will try to form here and there will be a shear plug type of damage that is going to occur out here. Okay. And then the inclined flexural crack will also propagate. Okay. So, in this way, okay, a normal simply supported system will behave during a blast loading event. Okay. And during this event the inherent properties of this material will undergo increase. Okay. The dynamic yield strength will increase, okay, and the toughness will also increase. Okay. So, continuing from the previous slide, the static material properties such as yield strength and the Young's modulus provide limited insight into the real world scenarios, okay, where the loading is rapid and intense. Okay. So, in a dynamic environment like automotive crashes, explosions, ballistic impacts, earthquakes, there are high strain rates. Okay. So, these events are having high strain rates. Okay. So, during this high strain rate, the material behavior, the static material behavior is modified. Okay. So, using the traditional quasi-static test, okay, this dynamic behavior cannot be efficiently measured. Okay. So, rate dependent hardening, inertia effect and the energy dissipation cannot be accurately observed by the static events. Okay. So, we will have to analyze this system due to a dynamic testing, okay, because if we test them in the dynamic environment only, then the energy absorption capacity, the failure modes can be assessed accurately. Okay. So, here we can see a comparison of the dynamic and the static tensile stress strain curve. Okay. So, here as we have seen, if we look into the dynamic testing, okay. So, dynamic testing are denoted by the square ones. So, dynamic, dynamic, dynamic. So, this three, these are the dynamic curves, okay, and these are the static curves. Okay. So, as we have seen, okay, if we compare the static curve with the dynamic curve, okay, the slope is changing, the slope is increasing, there is an increase in the yield stress and there is an increase in the ultimate stress. Okay. So, the properties in the static testing are very much different than the dynamic testing. Okay. Area under the curve is different, as well as the Young's modulus, the yield stress and the ultimate stress is different. Okay. So, for all the given materials, it needs to be properly evaluated using a dynamic testing facilities. Okay. So, the dynamic testing facilities are required in order to evaluate the properties of the materials during a dynamic scenarios like explosions and impacts. Okay. So, here we can see the blast simulation of a column, and here the dynamic properties of the columns are being used to model this thing accurately. So, engineering applications. So, in automotive sectors, okay, like in crumple zones, crash boxes, bumper reinforcements. So, they are designed to deform plastically and absorb kinetic energy. Okay. So, this type of systems, in this type of systems where their crashes are occurring, so the dynamic properties needs to be properly evaluated. Okay. Similarly, in aerospace structure where impact shielding is required, high amount of energy absorption is required in different components like seat mounts, landing gears. So, they are made from different type of materials, okay, like the toughened alloys are being used. So, there also the dynamic properties needs to be evaluated properly. In civil engineering structures, like in seismic dampers, like viscous dampers or metallic dampers that absorb earthquake energy, okay, there also the behavior of these materials, okay, and the dynamic events needs to be studied and that needs to be evaluated properly. Sacrificial cladding system in blast resistant design to protect structural elements. Okay. So, let us say what happens if we use the static properties. Okay. So, here we have seen the comparison between the dynamic properties and the static properties. Okay. So, in the static sense, if we measure the tensile strength, the yield strength, the ultimate strength, the area under the curve is different. Okay. So, if we want to efficiently design a sacrificial system, permanent system or a non-permanent system, then we need to estimate this thing properly. Okay. Otherwise, we will be overestimating the design. So, our design will not be lightweight and it will be a sluggish design. Okay. So, in case of automotive structure, this type of design will be highly unusable. Okay. So, a proper estimation of the properties of the material during a dynamic event is required. Okay. Similarly, bridge bearing and isolation pads designed with ductile metals and elastomers to deform under dynamic loading. Okay. So, these designs will become uneconomical or sometimes they will become unviable also. Okay. For a given configuration, this type of systems cannot be put into place because they will be very large. Okay. Because it has been evaluated using the static response, and in the static response, since the internal resistance and the toughness of a material and the absorption capacity is less, so then this system will become very large. Okay. So, similarly, the other examples are steel yielding devices in eccentrically braced frames and buckling resistance frames. Okay. So, here we can see in seismic resistance building this type of systems are being used. Okay. So, in order to design an efficient system that can be applied economically as that has economical viability as well as structural efficiency. So, the evaluation of the materials under dynamic loading is very much required. So, moving ahead. So, what are the challenges in study? So, we have established that the evaluation of the properties under dynamic loading is required, but how to do it? Okay. The first challenge comes from the high speed testing requirements. Okay. In a static loading, what is done? In a static loading, we can take a coupon, okay, and the coupon we can put it in a universal testing machine and try to pull it at a steady rate, okay, at a normal slow speed, okay, and that will give us a behavior of this metal in the static sense. But in a high speed testing requirement, okay, this needs to be pulled up with a very high speed, okay. So, this pulling up mechanism, okay, for this coupon is itself a challenge in order to be designed, okay. So, the testing requirements poses a big challenge here, okay. So, the dynamic event often occur in milliseconds, okay. So, if you look into blast loading, okay, if you look into blast loading or impact loading, okay, that whole duration of this loading is in milliseconds, okay. So, we need to test the materials in just a span of milliseconds, okay. So, since this dynamic loading is occurring in millisecond, the testing in order to find out the behavior of these materials, okay, under this loading has also been done under this millisecond testing configuration, okay. So, it requires special equipments, okay, such as SHPB or split Hopkinson pressure bars, okay. So, a special type of material is required or special type of equipment setup is required, okay, which is can be in the form of split Hopkinson pressure bar or drop weight testers, okay, which can replicate this type of blast or impact event, okay. They have also to give a very high amount of force in a very small amount of time, okay. So, in order to duplicate this type of dynamic conditions, the requirement of the special testing equipment is a must, okay. So, high strain rate conditions, okay, such as in the case of blast or impact load needs to be mimicked, for which the special type of testing equipments are required, okay. So, one is the specific requirements, okay, operational requirements are also there, but the setup requires precise instrumentation, okay. One is the part where special type of drop weight or some sort of split Hopkinson pressure bar is required, okay. So, this is one requirement, okay, special requirement for the testing facility. Also, we need to measure the quantities, okay. So, in order to measure these quantities, there is a precise requirement of the instruments, okay. So, here whatever strain gauges or accelerometers or force sensors, whatever we are trying to use, okay, they have to be designed for a dynamic event, okay, and the measurement, okay, such as the data acquisition system, they also need to be very fast such that they capture a large amount of data in terms of millisecond also, okay. So, the instrumentation or the measurement, that is also very costly, okay. And again the data reduction, the noise reduction also plays a picture, okay. So, the one requirement is the testing setup requirement and other requirement is the instrumentation requirement, and both are very costly, very time consuming to be achieved, okay. So, this is one part of the challenge of the study of the material under dynamic loading. So, requirement of the high speed testing facility, okay. So, special testing facility as well as the instrumentation requirement for that, okay. Next comes the material heterogeneity, okay. So, ductile materials often have non-uniform internal structures, okay, such as grain boundaries, inclusions, voids, okay. So, there as the making process goes, okay, they will have their own irregularities, okay. So, under high strain loading, this microstructural features behave unpredictability. Okay. Let us say we have a metallic coupon. Okay. So, during a static loading, okay, or during a very slow loading, we are sure that we are going to see a necking type of behavior. But this metallic coupon, okay, will have, or any type of ductile material will have certain irregularities. Okay. So, in the boundaries there will be irregularities, there will be impurities inbuilt into this system. Okay. So, that will not be engaged during a slow static event, but during a high dynamic event, this deformation, this impurities and all will play a significant features. Okay. So, under high strain rate, the failure modes can be engaged in any number of fashions. Okay. It is not that only I am going to see necking. Okay. If the impurities are there, the void formation can be there, and there can be a cracking in terms of the internal void formation also. So, this microstructural features, they will behave unpredictably. Okay. This is further augmented in case of composite or layered materials, okay, like in the sacrificial cladding system. Okay. So, interfaces will again exhibit complicated energy absorption mechanisms. Okay. So, there comes the challenge of unpredictable behavior. Okay. So, it gives rise to the non-repeatable behavior also. So, unpredictable, the behavior itself will be unpredictable, and there will be non-repeatability here. Okay. So, the material itself will behave in an erratic fashion. Okay. So, this is one more challenge of the study in the dynamic properties of a material subject to a dynamic loading. Okay. Then comes the modeling complexities. Okay. So, capturing the behavior of a ductile material under dynamic load in simulations required rate dependent material models. Okay. So, here what happened is, first the challenge was in devising an instrument, okay, that can mimic the effect of the dynamic loading. Then the challenge was in the instrumentation or the measurement of the body. Then the material, the ductile material formation process itself has different issues like grain formations, inclusions of the defects, voids, which will lead to the unpredictable failure modes as well as non-repeatable failure modes. Okay. Then somehow, even if we obtain the data, we have to make the material model. Okay. We have to make a mathematical rate dependent material model. Okay. So, they have to be transformed into the simulation world. Okay. So, in the simulation world, in the finite element world, this gathered data, okay, the data that we have gathered using the high speed testing requirement and minimizing the material unpredictability, whatever data we have given, we have to make the rate dependent material models. Okay. So, capturing this behavior, okay, mathematically is also a challenge in itself. Okay. And these material models also must account for the temperature effects, strain localization effects, crack initiation and propagation effects. Okay. So, this crack initiation propagation effects, temperature effects are normally not accounted during the testing procedures. Okay. So, these effects also have to be taken into account. Okay. Additionally, in a dynamic case, okay, we have to mesh our things. Okay. The finite element mesh has to be very fine in order to capture the complex behavior. Okay. So, there are different processes occurring, like spiling is occurring, crack initiation is occurring. So, this requires very fine meshing, and due to this fine meshing, the computational time goes a lot. Okay. So, the computational time also increases, and also a very high performance or a very high powerful computers is required to carry out the simulation. Okay. So, these are the challenges, okay, when we try to study the behavior of any system under a dynamic loading. So, it stems from the categorization of the materials under a dynamic loading, getting the data. Okay. In order to get the data, we have to design the experimental setup, we have to measure in the experimental setup, we have to measure such that the unpredictable failure modes are not there, the data is repeatable, and after that when we get it, we have to take into account when we try to put it into simulation. We have to develop the mathematical models, and this mathematical model should also cater for the other effects which are not accounted into the experiments, such as temperature effects and uncontrolled crack initiation and propagation process. Okay. And after that, when we have achieved all these things, okay, the finite element model that we are making, okay, that needs to have very fine mesh, which in turn increases the computational cost, and it requires a very powerful computation. Okay. So, that is why this entire process becomes lengthy, okay, and it is very complex in order to predict the proper behavior of a system under a dynamic loading. Okay. So, moving ahead. So, elastic and plastic deformation. So, elastic deformation is a temporary deformation. Material returns to its original shape once the load is removed. Okay. Normally, it follows Hooke's law. Okay. Stress is directly proportional to strain. Okay. So, it occurs below the yield point. We have already seen, okay, the first will be the proportional limit, and then there will be an elastic limit. Okay. And after that, there will be a yield regime. Okay. So, this is proportional limit where Hooke's law is obeyed. After that, there will be elastic limit, and after that the yielding will try to take place. So, the energy stored is elastically, and it can be fully recovered. Okay. It means that the material will recover to its original shape. Okay. So, here we can see a pictorial representation. Okay. So, this is the initial setup. Okay. Here, if the load applied, okay, is small enough, okay, then due to the Poisson's ratio, compression will occur in this phase and the elongation will occur in the other phases. Okay. And this is the deformation, and after the removal of the loading, this will come back to its original shape. So, this was the original position. During loading, this deformation occurs, and after that it goes back to its original shape. Okay. So, a steel wire slightly stretched under small weight springs back after loading. Okay. So, this is the linear elastic range. Okay. Loading, unloading phase, it comes back to its original shape. Okay. So, elastic, simply we can say it means reversible. Okay. So, what happens during a plastic deformation? In a plastic deformation, there is a permanent deformation. So, material does not return to its original shape. So, it begins after the yield point is crossed. So, after this yield point is crossed, the plastic deformation will starts to occur. So, it involves dislocation motion in the crystalline structure. So, if you look into the microstructure, okay. So, if you look into the microstructure, these things will remain in the same position, okay. But if it is in the plastic range, then the dislocation will try to occur. Okay. This micro regimes will move up in the other directions also. Okay. So, it will be not located in the same region. Okay. So, most energy is dissipated at heat or internal rearrangement. Okay. So, the bending of the copper wire, okay, if the copper wire bends and stays bent, and it shows large plastic deformation before failure. Okay. So, simply plastic deformation means the permanent deformation. Okay. So, here we can see we have started loading a structure. Okay. So, after it crosses into the plastic region, there is a elastoplastic deformation occurring, and once it returns, it does not return to its original shape. So, there is a residual permanent strain occurring here. Okay. So, even if the stress is removed, there is a permanent deformation occurring. So, this region is known as the plastic region. So, elastic region simply reversible, plastic region means permanent deformation has occurred. Okay. So, what is the relevance in terms of energy absorption? So, as we have already seen, ductile materials like steel, aluminum, copper, they can absorb high energy through plastic deformation. So, from the permanent deformation, the energy absorption takes place. Okay. So, this can be used in crash design, seismic field, okay, and they can be used in the forming shape and processes. The forming shape and processes results from the uniform occurrence of the material. Okay. There is no tensile chipping or something occurring in the surface. Okay, it will be a uniform shape. Okay. So, plastic is crucial in the dynamic loading scenario. Okay. So, whenever we have to design for the dynamic scenarios, a plastic deformation will be required. Okay. So, the deformation process. So, under the dynamic loading, material first responds elastically. Okay. So, it will start from here. Okay. So, the proportional limit will be reached, then the elastic limit will be reached, then the yield strength will be reached. So, as stress increases beyond elastic yield strength, as stresses goes from here, as it increases from here, they plastically deform, converting kinetic energy into the internal energy. So, here the plastic deformation is taking place, there is an increase in the stress. So, this is the strain hardening region, okay, and after that the necking region starts, and finally the fracture occurs. Okay, and the area under this curve is the total energy absorbed thing. Okay. So, this is the initial configuration of this bar, okay, and we are measuring between these 2 points. So, this is the original length. Okay. So, after that the necking region, as it increases, the necking region is forming, and the necking region is keeps on increasing, and finally the fracture will occur. Okay. So, this is how the plastic deformation will take place. Okay. So, we will stop here and continue in the next time. Thank you.